Last time we looked at the sampling distribution of a proportion. Today we're going to look at what the sampling distribution of the mean is. So we're going to start with a population of 1,000 points, or of 1,000 data points with a uniform distribution between 0 and 100. So as you can see, the average is a little over 50, as we expect. The standard deviation's 29.17. And you can see that the minimum value was 0.31 way down here, and the maximum was 99 point something way up here, 99.4. And so what I'm going to do is I'm going to draw a sample of size 1, meaning I'm just going to grab one data point and graph it. Okay? So if I do that, that one data point was between 18 and 20, and this shows the most recent sample down here, same thing. It turns out it was actually 18.32. If I draw one more, now my average is 32.62, but that's because my most recent point was up at 46.91. So when you average that with the previous one, you get an average of 32.62. Let's do a third one to make it a little more obvious. Now you can see that one of the data points I selected was between 15 and 20, another was between 20 and 25, another was between 45 and 50. Okay, let's do a fourth one. Another one between 15 and 20. And a fifth one. Oh, this one is way up here between 80 and 90. In fact, specifically, it was 89.92. I was waiting to see one that was up there pretty high. So that's our most recent sample. It was way up there at 89.92. And if I keep clicking this, I'll keep getting more and more, and eventually it'll kind of resemble this the original population. Let's try a sample size of 2. Let me clear all of that information. Again, drawing from this population. Okay, so if I do one of those, I draw it, and I get an average of 65.46 because the minimum value was 35.5 and the maximum was 95.42. And that's what they averaged out to be. It was a sample of two of them, a low number, 35.5, and a high number, 95.42. Let's try another one. Actually, let's do a third one. Now remember, each of these represents an X bar, an average for a sample of size 2. One of my averages was between 50 and, let's see what it would have been, 52. Another one was between 54 and 56. And another one was between 64 and 66. The most recent sample had a minimum of 50.94 right there and a maximum of 60.74. Of course, those were the actual 2 points. The average of those two should be around 56, 55 or 56. And sure enough, it was this one right here. Okay? So let's do a fourth one. And you can see that as I keep adding, oh, we had 2 of them between 75 and 80. But as I keep adding more and more, I've now got a grand total of 7 samples of size 2. And this is a histogram of their averages of their X bars. Okay? Let's suppose I do 1,000 of these draws. Okay? Again, of samples of size 2. It takes a moment. But you notice that they hump up in the middle. Very different from the original distribution. That's because the only way to get numbers out here is if both of them are high numbers. The only way to get numbers down here is if both numbers in the sample are low numbers. But if you have a high and a low, you'll be in the middle for the average. If you have a medium and a medium, you'll be in the middle. If you have a low and a medium, you'll be over here somewhere. If you have a high number and a medium number, you'll be over here somewhere. So they pile up in the middle, even for a sample of size 2. So what happens if we increase the sample size to, say, 36? That's a big jump, right? And again, we'll do it just one at a time. Let's delete the samples that we had there. Watch what happens. What would you expect to happen? Well, if we draw 36 at random from this population, our average, remember this is a histogram of 1 point, is 51.39. Why? Because our sample of 36 had 4 numbers between 0 and 10, 5 numbers between 10 and 20, 2 numbers between 20 and 30, and so on. And so all 36 of them have a minimum of 4 and a maximum of about 99, but the average ended up being 51. So right there in the middle. Let me draw 2 more samples. There's another one. Here's another one that always clarifies things. Notice how close together they are. They look far apart, but this is between 49 and 49.5, I think. 49.6 and 49.8, even tighter. This one's around 50.5, and this one's around 51.3. And so you can see that they're all clustered in the middle, even though the data itself is again spread out all over the place. The average for a sample of size 36 is like this. So if I click on a few more, we're up to 5, 6, 7, 8, 9, 10 samples of size 36. This is our most recent sample down here. Okay. And notice that they're all between around 45 and around 65. Okay. What happens if instead of drawing 1 sample at a time, I do 10 at a time? Well, watch what happens. They're clustering around 50. Okay. Let's do 100 at a time. So I'm now up to 120 samples. Oh, now they're really clustering. But is that really normal? Well, that's only 120 samples. If I overlay a normal curve, no, that's not even close. But this time, let's do 1,000 samples. So now we'll be up to 1,120. Now you can see how when we do 1,120 random samples, they do tend to cluster toward the middle, and they start taking on a normal shape. We can do even more than that. Let's do 5,000 on the next draw. 5,000 samples of size 36. And if we do that, it gets more and more normal looking. Okay. Let's do 10,000. So now we're up to 16,000 samples, and as you can see, those are samples of X bars. X bar is centered around 50, specifically 50.52, it says right here. Okay? And it's quite normally shaped. Here's the kicker. The standard deviation of the original population was about 29, just under 30. As you know, the standard deviation of the sampling distribution of X bar should be the standard deviation divided by the square root of the sample size. Our sample size was 36. Okay? The standard deviation over the square root of 36 is just under 30 divided by 6, which should be just under 5, and there it is, 4.83. So the X bars from all those 16,000 samples of size 36 cluster around the same mean, 50. In fact, it has the same mean out to the 100th. That's pretty surprising. But with a much tighter standard deviation and with a much more normal shape. By the way, the last of those 16,120 samples still was drawn from the entire population from 0 up to 100. But the process of averaging and the central limit theorem tells us that X bar is going to be more normal with the same mean, 50, but now a standard deviation of S over the square root of N. And that's the sampling distribution of the mean. Thanks.